In this video, we will look at sensitivity methods for nonlinear equations. We will look at finite differences, forward sensitivities, as well as adjoint sensitivities with this simple coding example in Python. Let's get started. Hi and welcome to this new video. A nonlinear equation is a simple case for a nonlinear system of equations, and here we want to look at it in this residual form. I've chosen this rather simplistic example which depends on the variable u, which this residual function has to be solved for, as well as a parameter theta. Then we will have a root finding algorithm for which we are going to use SciPy, which solves this residual in terms of u and gives us a u given a certain parameter theta. This u will then enter a loss functional, so you can think of it as, for instance, an L2 loss. Here it's just the square of whatever value we got out. And then we are interested in a derivative information, since obviously the value of theta affects the value of u and thereby affects the value of the loss functional j. And we are interested in the derivative or the gradient information dj by d theta. And this information might be helpful for gradient-based optimization or for local sensitivity analysis. The most naive approach in obtaining these derivative information is using finite differences. For this, you just evaluate the loss functional at a slightly augmented position. So we assume we have this hypothetical function f, which evaluates the root finding method and thereby gets us a u star dependent on the particular theta star we enter there. And then we will just compare an augmented loss functional with an unaugmented one and then divide this by a small step length, usually 10 to the minus 6. Then we are also interested in sensitivity methods which are precise up to machine precision. The first one we want to look at is forward sensitivities, which consists of the 3 steps. We first have to solve the classical problem, so that's just like evaluating the root at the particular theta position. Then we will solve for the solution sensitivities, which is a du by d theta quantity. And here we have to evaluate 2 more derivatives, the derivative of the residual with respect to u, as well as the derivative of the residual with respect to theta. Once we then have these solution sensitivities, we can then plug them in order to obtain the loss sensitivities. If you want more detail on the derivation and also for the upcoming adjoint sensitivities, then check out the video I've linked in the top right here, where I do these derivations in case of a nonlinear system of equations. The adjoint sensitivities are another approach here. For this, we also first have to solve the classical problem, so a usual forward evaluation, and then we obtain an adjoint variable for which we have to solve a different problem than in the forward sensitivities, and this adjoint variable, usually called lambda, can then be used in order to obtain the loss sensitivities, so the gradient information we are interested in. And then we are going to write some code. I already have that here, but we will write it in a second. And then you can execute that file, so you can run the code by saying Python adjoint nonlinear equation, and then it gives you a couple of printouts. We are more interested in the last 3, which is a particular gradient value, and there we are going to compare finite differences with the forward and adjoint method. So let's delete all the code and let's start from scratch. Okay, here we are with a blank file except for the doc string. Then let's start with our imports. So we will need numpy, s, and p. And as said, we're going to use SciPy for the root finding. So let's say from SciPy import optimize. Then let's create a main switch. So if underscore name equals underscore main, then execute the main function. And let's create a main function. And then we can start. So I first want to implement the residual function. So let's define a function that is called residual. And this one takes a u as well as a theta. And it is a residual in terms of u, which is parameterized by theta. Both are scalars here for the simplest case possible. And the one I want to implement here is u squared minus the sine of theta. And then we have our residual, so this is basically this r function here, And then in order to have an easier life later on, I also want to implement the f function. So this f function is kind of a wrapper around a call to the root finding algorithm, which obtains a u star given a theta star. And I want to call this function obtain root, and this one takes theta and returns a u. In order to query our root finding algorithm, well, we do optimize dot root scalar, and then we have to provide a couple of arguments. So first it wants an f. So here the interface to SciPy is called f, but this essentially is just a residual function. However, the interface to SciPy is that this function shall only take one argument, which is the unknown it is based upon. And in order to wrap our residual, I want to use a lambda function. So I will say f equals lambda u. So have an anonymous function that just depends on u, which calls the residual on u and plugs in the theta value as given here. So we are just wrapping the interface to this residual here. And then in order to use an efficient algorithm here, I will also provide an initial guess. So we will have an x0, and I just want to call this u0 here and define it before the call to the root finding. So let's say, for instance, u0 is 1.0. And that's, of course, let's say a wild guess. And typically, if you solve nonlinear problems and also larger nonlinear systems, this is a crucial point where you have to be careful. So I just want to add that here. Usually the initial guess is crucial, especially if you have multimodal problems. However, here I rather want to focus on sensitivity methods, and I'm assuming that this function always works, which is of course a strong assumption. And then in order to have a rather efficient algorithm, I also want to provide the f prime, which is the derivative of the residual with respect to u. And since we will need these derivatives later on anyways, let's define separate functions for them. So let's have a function which is the partial derivative of the residual with respect to u. And of course, this is still a function that depends on u and theta. So if you take the derivative of u squared minus sine of theta with respect to u, you will get 2 times u. Well, of course, now you could argue this is no longer a function of theta. However, it could still be a function of theta. For instance, if we had a multiplied theta in here, or whatever kind of functional form you can come up with. And for completion, let me also put down the other partial derivative. So the derivative of the residual with respect to theta, which is also, let's say for generality, also still a function on u and theta. And if we take the partial derivative of u squared minus sine of theta with respect to theta, this will of course be minus cosine of theta. Well, anyways, now we have the derivative of the residual with respect to u, which is the f prime we hand over to the root scalar function. And we again have to wrap it here because it had 2 arguments and this is only allowing 1 argument. So I will again use a lambda anonymous function and say u, and then we will do del residual del u and plug in u and fix theta to theta. And this will then vary the root finding algorithm. It will use a suitable algorithm for us. And the returning object I want to call root finding result. And this is kind of a container with a lot of stuff in it. For instance, some diagnostic information on the algorithm, but I don't want to go into too much detail. I just want to add a switch here in order to make sure that our root finding algorithm converged. So let's say assert, and which is probably the easiest way to do that, root finding result dot converged. And this dot converged is a boolean, which is true if the root finding converged and false if not, and this assert will interrupt the execution of the file if it was false. And if it's true, then let's continue, and then I want to return root finding result dot root. So this is just the functional value we're getting out here. Then let's define an evaluation point, and by this evaluation point I mean, this is the theta value. So this is, let's say, one particular theta value. And then let's, for instance, query the u at evaluation point. And for this, we use the function obtain root. We just created and say it at evaluation point. And then let's print this and say with a formatted string u at evaluation point equals, and then let's have that one printed out and do 1.6 precision floating point numbers. Let's save that for a second so that we can see what the function is doing so far. Let's execute that. And here we go. So we see that if we use a theta value of 1.0, then the root, or one root of the problem, is 0.91. If we were to change that, for instance, to 2, we will get a different result. And here you go, it's slightly different. I want to go back to 1 here. Okay, so this is basically the residual together with the hypothetical function f, which we called obtain root here. Now I also want to implement the loss functional, which takes the solution from the root finding algorithm and then produces a loss metric. So let's close down the terminal for a second and implement a function, let's say loss functional, and this one takes a u, so a solution, and it will just return the square of it. Super simple. And later on, we will then also need derivatives of this one. And this is, of course, the partial derivative with respect to their arguments. So let's define del j with respect to u, which will still be a function based on u. And of course, it returns 2 times u, which is the derivative of the loss functional. Okay, let's also evaluate that in order to get a feeling for it and say j at evaluation point. And this will, of course, be the loss functional called on u at evaluation point. Then let me just copy that here and swap out the names. So this will be j at evaluation point. And then we also have j here. And then if we execute that again, then we see first we have our solution value given the particular parameter value as well as the loss functional. And then we can start with our first sensitivity method. So let me close down the terminal again and call this the finite differences section. And as said, this is the easiest way to obtain it, but unfortunately also the least accurate way. And for this, I have to define an epsilon, or a small step length, which I said will be 10 to the minus 6. So just a small number. And then we can define dj by d theta finite differences, which will be given as the loss functional evaluated at obtain root at the evaluation point plus the epsilon. And then we subtract from that the loss functional evaluated at obtain root at the evaluation point. And then we divide that by this step length. So we just go a small amount into the epsilon direction and then subtract it from this original value and then divide it by epsilon. Then let's print that out and say print with a formatted string and use first the value. So we will have dj by d theta finite differences. And I want to use 16 digits after the comma, such that we can properly compare it with the other measures here. And then say this is a finite differences derivative. Then let's also quickly check whether we did any mistakes. So let me run it. And here we go. So this is our first derivative value we got. Well, of course, so far it's just standing there. Let's try it with the other measures. For this, let me go on with first the forward sensitivities. And for the forward sensitivities, we first have to solve the classical problem. So obtain a root given our evaluation point. So this will be, I want to call it u classical, and call obtain root on the evaluation point. So this is our theta star, and this is our u star from now on. Then we can obtain the solution sensitivity, which was the du by d theta, and this one is given as minus 1 divided by del residual del u evaluated at u classical and the evaluation point, and I want to make this more verbose and say theta equals evaluation point, and then multiply that with the del residual del theta at u classical and theta being the evaluation point, and let me put that into a new line here. And I just want to leave one note here, which is quite crucial. And if you look at the algorithm here, you see I'm using this notation with a raised to the minus 1, which in a scalar case would indicate inversion, so we divide by it. And this is also one of the simplifying cases that we have here when we look at nonlinear equations. If you had a nonlinear system of equation, you had to solve a linear system of equation here, because that would turn out to be a matrix, and so it might be a bit more challenging here. But since we look at the simplified case, we can just divide by it. But be advised that it can become more challenging in higher dimensions. And also feel free to look at the subsequent videos where we will solve it for a system of equations to also get a feeling for that. Anyways, let's continue with the third step to obtain our loss sensitivities. So this will be dj by d theta forward. And for this, we have to evaluate the del j by del u, so the partial derivative of the loss functional with respect to the solution. And we evaluate it at u classical and multiply that with the solution sensitivity. And then let's print out what we have. Again, formatted string, and then have dj by d theta forward. I want to use, again, 16 digits after the comma precision, and then say this is the forward derivative. And let's also quickly check on the implementation. Here we go. We will discuss it in a second. At least it works for now. And then lastly, let's do the adjoint sensitivities. So adjoint sensitivities. And for the adjoint sensitivities, we as well have to first evaluate the classical problem. So u classical equals obtain root at the evaluation point. Then we have to obtain our adjoint variable. This was the lambda. And here again, we actually had to solve an inversion. So for nonlinear systems, this would be a solution to a linear system of equations. However, here we can again divide. So we will do 1 divided by del residual del u on u classical as well as theta being at the evaluation point. And then multiply this inversion with del j del u evaluated at u classical. And then once we have the adjoint variable, we can obtain our loss sensitivities dj by d theta adjoint. So what we're going to do is say minus del residual del theta, the adjoint variable multiplied with del residual del theta evaluated at u classical and theta being at the evaluation point. Let's also print out the result of that. So again, formatted string, and then do dj by d theta adjoint, and with 16 points after the comma, and then say adjoint derivative. Then let's bring up the terminal again and finally evaluate that. Here we go. Now we have 3 different derivative measures, and if you look at the digits after the comma, the forward and adjoint method are identical, whereas they differ from the finite difference way. And the finite difference is precise up to, let's say, 5 or 6 digits after the comma here, and then it deviates. And in this particular problem here, we can argue that the forward and the adjoint method are precise up to machine precision, and actually the precision of the gradient estimate depends on the precision or the tolerances used in the root finding algorithm here. So the tolerances that you hand over to the SciPy algorithm. And of course, and this goes without saying, that these methods, also including finite differences, only work if the root finding algorithm converges. And that's of course something that we assumed here. I don't want to do any timings here because it does not make much sense in this scalar valued case. We will do that once we look at the nonlinear system of equations, because then we can also see the scaling effect, and there we will clearly see that the adjoint method is the fastest approach that one can use once the problems reach a certain size. On top of that, also one thing that I want to notice here, if you look at the computations that happen in the forward sensitivities and the adjoint sensitivities approach, and if you were to like simplify the computations, you would see that those are identical. In both times, we divide by del residual del u here. And that's of course because we are in this univariate, in this scalar valued case. However, the advantage comes clear once we see the high dimensional cases, and then we have to solve the linear systems of equations. And there it will turn out that the adjoint method is more efficient, since the del j by del u will always just be one vector, whereas the del residual del theta will turn out to be a matrix, and thereby introduces a batched solve of linear systems of equations. I hope this small example gave a little bit more light on the adjoint methods and forward sensitivity methods for nonlinear equations. You can download the script with the link in the video description. If you enjoyed this video, then please leave a like and consider subscribing to the channel. There's more content on this stuff with automatic differentiation, adjoint methods, and so on. And also check out the next video where we will use the JAX deep learning framework in order to avoid writing down these handwritten derivatives. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed it. Here you will now see similar videos, and then I hope to see you in the next videos.